Considering the Carnot cycle as applied to a liquid film, show that in an isothermal process, heat required in formation of a unit area is given by minus T d alpha by dt. So alpha is surface tension. So Carnot cycle as applied to a liquid film. So when we apply Carnot cycle to a gas, we plot P versus V. But because we are applying it to a liquid film, let's plot S versus A. So why S versus A? Because if you remember, in gaseous Carnot cycle, area PdV gave the work. Here, excuse me, here the work done will be the area of SA curve. So work done on the film by an external agent is integral SdA. That is area under SA curve. So we are plotting S versus A, and we know that at a given temperature, surface tension is constant. So our two isothermal lines will be like this. And then we have two adiabatic lines. So let's connect them like that. So they are straight because we are considering a very small Carnot cycle. So adiabatic processes, these two, and for a very small cycle, they are assumed straight and parallel. See, what we need to find is ds d alpha by dt. So we are going for a small increment in temperature. So that's why our Carnot cycle is quite small. Now let's take this point, and let's say surface tension is S and area of the film at this point is A. So as the temperature decreases, surface tension will increase. So it will go from here to here, and here temperature will be T minus dt, less than this. Up to here, then again there will be adiabatic process, and as the area reduces, the temperature will increase, and when temperature increases, surface tension will decrease. So you might be wondering why this line is like this and not like this, right? How do we know that when we increase the area, temperature does not increase? So for that, we are just referring to this note here, that when area of the film is increased adiabatically, temperature reduces. So why this happens, that is beyond our scope, but just know that this curve is going to go like this and not like this. Even though if you don't know this concept and you draw the adiabatic lines like this, your answer will still come the same. But this is more accurate, where we know that whenever we have an adiabatic change in area, then when the area reduces, temperature increases. And when area increases, temperature reduces. So why we have to consider Carnot cycle to arrive at this derivation? So you can see we have a term of Q here, that is heat, and this is heat required. So this is the input heat, not the waste heat. So the input heat is given in this formula, and T and dt. So the ratio of dt by T is given. So if you remember, for the Carnot cycle, efficiency is dt by T. And when we are talking about efficiency, then there is a term of work done upon Q. So we have got three of those terms, Q, T and dt, that relate to the Carnot cycle. So let's use that help to arrive at this formula. So only term here missing is work done. So let's start from there. So work done on film we know is integral SdA, that is the area under this curve. So for the whole cycle, integral of SdA will be the area of this parallelogram, and that area will be ds into dA, because area of this parallelogram is same as area of this rectangle, and that area is dA into ds. So work done on this film for the small Carnot cycle is ds into dA. Now let us use our equation for efficiency, that is dt by T, that is work done by film upon dq. So because we have to write work done by film, that will be negative of work done on film. So this becomes minus ds dA by dq1. And what we need, so this q is heat required to form per unit area. So in our equation, this term q will be dq by dA, and that you can see will come to be minus T ds by dt as required. Hence proved.